I welcome you all in the seventh lecture on camps and followers. In this lecture, we shall be exploring the displacement, velocity, acceleration, and jerk phenomena of a follower which is moving with a cycloidal manner. We shall also be discussing about how the displacement diagram for a follower which is moving with cycloidic motion is developed. So let us first understand what a cycloid is. A cycloid is a curve traced by a point on the circumference of a circle when the circle rolls without slipping on a straight line. As you would notice in the figure 1, there is a straight line marked here with this black color. There is a circle which is shown here by green color, and there is a point that is a red point marked on this circle. So this circle is basically in contact with this straight line at this point of contact. Now what this circle does now, the circle starts rolling on this line without slipping. So these are the different positions of the circle when it rolls on the straight line. We just focus on this first point of contact of this circle with the straight line. So we observe that this point of contact of circle with the straight line, as the circle rolls on the straight line, the trajectory of this particular point is basically along this red path, and once the circle completes one rotation, again this particular point comes in contact with the straight line again. As you would clearly notice it from the animation 1 and animation 2 here, that there is a circle which is rolling on this straight line. Initially the point of contact of this circle with the straight line is marked as this red point, and this red point basically travels along this path, and again it comes back to the contact of this straight line as the circle makes it one complete rotation. Animation 2 is basically more clearer in this way to explaining how the cycloid is developed. There is a circle which is rolling on this straight line. The initial point of contact is basically moving along this particular path, and this path is nothing but the cycloid. So we have seen that when a circle point that is basically a cycloid is a curve traced by a point on the circumference of a circle when the circle rolls without slipping on a straight line. So when we apply this phenomena of cycloidal motion to the cam and follower, we notice that this straight line is basically nothing but the stroke of the follower. Stroke means the total lift imparted to the follower, that is the rise or fall of the follower is nothing but this straight line. And because this circle in one rotation basically moves along this straight line and it completes a distance of s, so obviously this 2 pi r, that is the circumference of this circle, is going to be equal to the stroke length. So from here we can determine the radius of the circle as s upon 2 pi. Now we shall be developing the expressions for the displacement, velocity, acceleration, and jerk for a follower which is moving with the cycloidal motion using the analytical approach. So in the previous slide we have seen that a cycloid is nothing but a curve which is traced by a point on the circumference of a circle which rolls on a straight line. So here this straight line is nothing but a line which is equal to the stroke length of the follower. For the sake of understanding, we have considered this stroke length to be equal to 66 units. So what we are going to do here is, since we saw that the radius of the circle which rolls on this straight line is basically r is equal to s upon 2 pi, where value of the s is 66 unit. So when we divide it by 2 pi, what we get is the radius of the circle comes out to be 10.5 units. So diameter of the circle is going to be 21 units. So initially the circle is in contact with this straight line at point number A. As this circle rolls on this particular line, on this straight line, the point number A basically moves along this particular path. So when the circle rolls along this line, the lift of the follower is basically obtained by having the projection of these different points A1, A2, A3, A4 and so on this straight line. So the motion of the follower is quite similar to that, because when the cam turns through an angle equal to the outstroke angle, means when the cam rotation angle varies from 0 to theta naught, the follower gets lifted up completely. It takes its full rise. So we can notice it from the figure number 2 here. Initially there is a straight line. Its length is going to be equal to the stroke or the rise of the follower. There is a circle whose radius AB is r, and it is equal to s upon 2 pi. So initially the line AB is in contact with this straight line, which is nothing but the stroke of the follower at point number O. Now this circle starts rolling on this straight line. So after a certain while, when this line AB makes an angle of phi from its original position when the circle was right here, and its point of contact of this line AB was at point number O. So this is going to make an angle of phi, and the new position of the point number B, now it becomes A dash and B dash. So what we do here is we take the projection of the point B dash on this straight line, and its projection comes out to be somewhat here. So it's basically at point number C. So this distance AC is nothing but the displacement of the follower when the circle has rolled through an angle of phi, or the cam has turned through an angle of theta. Because when the cam completes its rotation by theta naught, that is when the cam rotation angle is equal to the outstroke angle, the follower gets lifted up completely, means it completes its rise. So obviously we can now express this phi in terms of theta. So how do we do that? Because we have seen that when theta is equal to theta naught, so basically the circle makes one complete rotation. So phi is going to be varying from 0 to 2 pi when the theta varies from that is 0 to theta naught. So we can have a relationship between phi and theta like this. So phi is going to be expressed as 2 pi upon theta naught into theta. So we see that at any point of time when this line AB has turned through an angle of phi, or the cam has turned through an angle of theta, the displacement of the follower is equal to y. So y is nothing but equal to the distance AC here. So AC can be calculated by A dash minus A dash into C. So displacement of the follower at any point of time when the cam has turned through an angle of theta from the 0 degree angle. So y is going to be AC, and it is given as A dash minus A dash into C. So A dash, what is A dash here? A dash. So we can precisely notice that A dash is going to be defined as A dash. So when we look at the distance, that is O dash and B dash, this arc length is basically equal to what? O dash. So we can easily calculate this. So we notice that this the length arc length along this circle, that is O dash into B dash, is equal to O dash into O. So this arc length is nothing but, that is arc length is given by r into phi. R is the radius of this circle multiplied by the angle. So that is how we determine this arc length. So arc length is going to be this r into phi. So when we take a product of this, s upon 2 pi into 2 pi upon theta naught into theta, so that gives us a value of A dash here as theta by theta naught into s, minus A dash into C. A dash into C, you would notice it that it is nothing but r sine 2 pi upon theta naught into theta. So now we can check the continuity of this equation 1, which is nothing but the equation for the displacement of the follower at various positions of the cam. So when the cam has just started rotating, so initially it makes an angle of theta equal to 0 degree. When the cam has turned through an angle of that is half of the outstroke angle, and when it has completed the outstroke angle. So we can check out the values of y at different values of theta. So when we do so, what we get is the y at theta equal to 0 is 0, which is quite obvious because when the cam just starts rotating, the displacement of the follower is 0. When the cam has turned through an angle theta equal to theta naught by 2, that is half of the outstroke angle, what we get is it is equal to, when we substitute the value of theta here as theta naught by 2. So what we get is the displacement imparted to the follower is s by 2, which has to be so because when the cam has turned through an angle of half of the outstroke angle, the follower would complete a distance that is half of its total lift. So it is going to be s by 2. When the cam has turned through an angle equal to its outstroke angle, the y that is the displacement of the follower becomes equal to s. That is, the total lift has been imparted to the follower. So the equation that we have expressed for the displacement of the follower by equation number 1 is exactly okay. Now we can further differentiate the expression for the displacement of the follower, that is y, with respect to time, in order to determine the velocity of the follower. So we can differentiate this expression y with respect to time. So it gives us the velocity dy upon dt. So when the differentiation is over, what we get is we get the expression for the velocity of the follower given by the equation number 2. So remember that the velocity is basically going to be a function of the cam rotation angle, because s is constant, the total lift imparted to the follower is constant, the angular velocity of the cam is constant, theta naught, that is outstroke angle of the cam, is also a constant value. So there is a relationship between this velocity of the follower with theta, that is the cam rotation angle. You need to remember still that the radius of the circle which rolls on that straight line is equal to s upon 2 pi. So now we can check out the values of the velocity imparted to the follower at different cam rotation angles. So we can check out the value of this velocity at theta equal to 0, when theta is equal to, that is 1/4 of the outstroke angle, when theta is equal to half of the outstroke angle, when theta is equal to 3/4 of the outstroke angle, and when finally the cam rotation angle is equal to the outstroke angle itself. So when we do so, we observe that by putting theta equal to 0 in this equation number 3, the velocity of the follower is 0. So initially the follower is at rest. At the half of the outstroke, quarter of the outstroke angle, the velocity of the follower is given by the expression s upon theta naught into omega. At the half of the outstroke angle of the cam, the velocity of the follower is given by twice s upon theta naught into omega. And at the 3/4 of this outstroke angle, the velocity becomes s by theta naught into omega. And finally, when the cam has turned through an angle equal to its outstroke angle, so velocity of the follower is again going to be 0. So we observe that the velocity of this particular follower is going to attain its maximum value when this bracketed quantity in the equation number 3, this quantity is going to attain its maximum value, because s is constant, omega is constant, and theta naught is constant. So when this bracketed quantity is going to attain its maximum value, the velocity of the follower will also be maximum. So for that purpose, what we notice here is that cos of 2 pi upon theta naught into theta from here is going to be equal to -1, and we determine the value of theta as theta naught by 2. So which is quite obvious. When the cam turns through an angle equal to half of this outstroke angle, the follower attains its maximum velocity, that we have already noticed that its value is given as twice as theta naught into omega. Now we can further differentiate the equation number 3 with respect to time, or the equation number 1 that was given for the displacement imparted to the follower, that is with respect to time, that is we can have the second differentiation of that. So that will ultimately give us the acceleration of the follower. So it is going to be d2y upon dt square, or simply the dv upon dt. So having done that, what we obtain finally is the expression for the acceleration imparted to the follower. So it is given by this particular expression, and let us call it as equation number 5. We can now check out the values of acceleration at again the different values of the cam rotation angle. So when theta is 0, when theta is equal to theta naught by 4, that is 1/4 of the outstroke angle. When theta is equal to half of the outstroke angle, when theta is equal to, that is 3/4 of the outstroke angle, and when theta is equal to theta naught, means when the cam completes its complete outstroke. So we observe that the by inserting the value of theta equal to 0, theta equal to theta naught by 4, and so on, the values of the acceleration are obtained as 0, means when the velocity of the follower is 0, the acceleration has to be 0. So at theta equal to theta naught by 4, the acceleration has got a finite value, which is given by 2 pi s upon theta naught square into omega square. At half of this outstroke angle covered by the cam, the acceleration of the follower is again 0. When the cam turns through an angle of 3/4 of its outstroke angle, the acceleration is going to be negative now, but the magnitude is same. The magnitude that we had at theta equal to theta naught by 4, same is the magnitude at theta equal to 3 by 4 theta naught, but it is with a negative sign. And again we observe that when the cam completes its outstroke, when theta is equal to theta naught, the acceleration of the follower is 0. So obviously the maximum acceleration will occur when sine of 2 pi upon theta naught into theta is maximum. So we can determine the value of theta where we get the maximum acceleration of the follower. So when we do so, by putting that condition, sine 2 pi upon theta naught into theta equal to 1, what we get is when theta is going to equal to theta naught by 4, that is 1/4, 1/4 of the outstroke angle, the acceleration of the follower is going to be maximum, and we determine its maximum value as 2 pi s upon theta naught square into omega square. So that is the value that we obtained in the equation number 6. So the point which is to be noted about the acceleration of the follower is that nowhere we found the acceleration to be infinite. It is initially when theta is 0, the acceleration of the follower was 0. Then it acquires a finite value equal to 2 pi s upon theta naught square into omega square when the cam turns through an angle of 1/4 of the outstroke angle. Again, at the mid of this stroke, the mid of the outstroke, the acceleration of the follower is 0. Again, at the 3/4 of the outstroke angle, the acceleration is with a negative sign, but again it is maximum. And when the cam completes its outstroke, the acceleration imparted to the follower is 0. So the nowhere at different cam rotation angle values we obtained the acceleration to be infinite. That is very important feature of the cycloidal type of the motion of the follower. Now we further differentiate the expression for the displacement, means we are going to have the third differentiation of the displacement of the follower with respect to time in order to determine the value of the jerk imparted to the follower, or we can further differentiate the expression for the acceleration with respect to time. So when we do so, finally what we get is the expression for the jerk. So it is going to be basically a cosine wave. So it is given by the expression this 4 pi square s upon theta naught cube into omega cube cos of 2 pi upon theta naught into theta. So this is very important equation given by equation number 8. So this is basically a equation which establishes a relationship between the jerk imparted to the follower at different cam rotation angle theta. So we again check out the values of the jerk imparted to the follower at various cam rotation angles. So by inserting the values of theta equal to 0, theta equal to theta naught by 4, theta equal to theta naught by 2, and so on. So when we do so, we observe that the jerk imparted to the follower when the cam just starts rotating its or undergoing its outstroke angle, it is at the beginning of that, and the follower just starts getting lifted up. The that is the jerk imparted to the follower is not infinite. So it is going to attain a finite value. It is equal to 4 pi square s upon theta naught cube into omega cube. At 1/4 of this outstroke angle, the jerk imparted to the follower is 0. At half of this outstroke angle, the jerk imparted to the follower is this much, but with a negative sign. And at 3/4 of this outstroke angle, again the jerk becomes 0. And when the cam completes its outstroke angle, the value of the jerk is this much. So this is my equation number 9. So now we can have a plot of all these four variables, that is displacement of the follower, velocity of the follower, then acceleration of the follower, and finally the jerk imparted to the follower, plotted against a cam rotation angle for its outstroke angle. So here along this x-axis or abscissa, the cam rotation angle is taken and its value varies from 0 to theta naught here. Along this y-axis, we are having the different curves plotted for the displacement, for velocity, for acceleration, and for jerk. So when we do so, we first plot the variation of this, that is the displacement imparted to the follower as the cam undergoes a rotation equal to its outstroke angle. So this is going to be the path. This is going to be the path, means at different cam angles, these are going to be the lift values imparted to the follower. And finally, when the cam completes its outstroke angle, the follower is at its peak, means follower has been lifted up completely. So this is the total lift imparted to the follower, which is equal to its outstroke value given by S. So this is going to be the displacement diagram. Next, we look at the velocity. We observed that the velocity when theta was 0 degree, the velocity of the follower was 0, and when theta was equal to theta naught, the velocity was 0. At the mid of that, when the cam completes half of its outstroke angle, the velocity of the follower was maximum. So this is going to be the variation of the velocity curve for a follower which is moving with cycloidal fashion. Then we look at the acceleration. This is very important to see the variation of the acceleration, because finally what we get is it's basically a sine curve. So initially when theta is 0, the cam just starts undergoing its outstroke angle, the acceleration is 0. It attains its maximum value when theta is equal to theta naught by 4, that is 1/4 of its outstroke angle. When theta is equal to theta naught by 2, at the mid of the outstroke angle, the acceleration is 0. When the cam completes its that is 3/4 of the outstroke angle, the acceleration changes its sign, but its magnitude is same as it was having at theta equal to theta naught by 4. And again, when theta is equal to theta naught, means when the cam has completed its outstroke angle, the acceleration of the follower is 0. So this is very important feature of this cycloidal motion of a follower, because nowhere we see that the acceleration attains a infinite value. So it is always having a 0 value, then goes to maximum, then again passes to 0, again attains a maximum value in negative direction, and again it becomes 0. Then we finally notice the variation of the jerk imparted to the follower when theta is 0 degree. We observed that the jerk imparted to the follower was not infinite. So it is having a finite value when the cam just starts rotating and follower starts getting lifted up. Then gradually its value comes down to 0 when theta is equal to theta naught by 4. Then it becomes maximum in the negative direction with this much of magnitude, and when theta is equal to 3 by 4 of theta naught, that is 3/4 of the outstroke angle, the jerk imparted to the follower is again 0. And when the cam completes its outstroke angle, the jerk is having only a finite value. It is not an infinite value. So it is noticed that for these four type of displacement curves, because we have gone through the four cases of the motion of the follower. That is, first case was when the follower was supposed to be moving with uniform velocity or the constant velocity. Second case was the follower when it was supposed to be moving with uniform acceleration and retardation. Third case was the follower with the simple harmonic motion, and fourth case that we are discussing right now is the motion of a follower with a cycloidal manner. So it is noticed that for these four type of displacement curves and its three derivatives for velocity, acceleration, and jerk, the jerk curve for cycloidal motion has a finite value throughout the cam operation cycle. So thus the cycloidal curve is the best of these four curves discussed so far. Here we can notice the displacement of a follower moving with the cycloidal manner, also its velocity, acceleration, and jerk for one complete rotation of the cam. Mean when the cam undergoes a rotation from 0 to 360 degree. We notice that the cam starts pushing it out. That is, the follower starts rising up at 20-degree rotation of the cam. So this is the point from where the cam starts pushing out the follower. So basically, it moves along. It is going to attain these much of that is the lift positions at different values of the cam rotation angle. So this is basically going to be the outstroke rotation of the cam. So during this outstroke angle, the follower basically attains the different lift position values, and finally it is at the maximum lifted condition, or it attains a lift equal to its outstroke. Then the cam observes a dwell period. So during this first dwell period, there is no motion imparted to the follower, so its displacement is going to be zero. So it remains at that condition only. And during this angle, the movement of the cam from 200 degrees to 340 degree, this is basically the return of the follower. So follower again comes down to its original position, and further it follows a second dwell period. So this is going to be the variation of the velocity. So as we discussed earlier in the previous slide, that at the mid of the outstroke angle, the follower is going to attain the maximum velocity, but the zero acceleration, but the highest value of the jerk in negative direction. So acceleration in this particular variation for one complete rotation of the cam, we notice that nowhere the acceleration is going to attain an infinite value. It is always having a limited value of acceleration. So it is initially when the cam starts rotating, undergoing its outstroke angle, initially the acceleration is zero. Then at theta equal to theta naught by 4, the acceleration is maximum. At theta equal to theta naught by 2, that is midway of the outstroke, the acceleration is zero, and again the acceleration is zero at the end of the outstroke angle. Similar is the variation during the return stroke, but it is going to be the mirror image of the curve that we obtained for the rise or the lifting condition of the follower. Jerk phenomena, we have seen that the initially when theta is 0, the jerk is having a finite value, then it starts decreasing. At theta equal to theta naught by 4, the jerk is 0. When theta is equal to theta naught by 2, that is at the mid of the outstroke angle, jerk is having a maximum value but with negative sign. Then at theta equal to theta, that is 3 by 4 of theta naught, the jerk is 0. And again, when the cam completes its outstroke angle, follower has been lifted up completely, jerk is having only a finite or limited value here. So this is the variation of that is the velocity, acceleration, and jerk imparted to the follower when it is moving with a cycloidal manner. So now we can always remember certain points for the motion of the follower with the cycloidal motion. First is that in a physical sense, it is the motion of a point on a disk rolling on a straight line. Cycloidal motion is another motion scheme derived from the trigonometrical functions. This scheme exhibits very smooth motion curves and does not have the sudden change in acceleration at the ends of the motion, which makes it popular for high-speed applications. The jerk curve for cycloidal motion has a finite value throughout the cam operation cycle. Thus, cycloidal curve is the best of these four curves discussed so far. It has low vibration, wear, and stress characteristics of all the basic curves described. Now we shall be discussing about how the displacement diagram for follower moving with cycloidal motion is generated. So as you would notice in this particular figure that along this abscissa we have taken the cam rotation for its outstroke. So the total length taken along this x-axis or the abscissa up to this point number 6 is equal to the outstroke angle or the time required to complete that outstroke angle. So either it is equal to theta naught or t naught, because angular velocity of the cam is constant. So either we go for taking the value of theta naught along the x-axis or t naught, it is one and the same thing. So suppose the outstroke angle of the cam is say 90 degree. So what we are going to do here is we will assume some suitable scale for marking the cam rotation angle, that is outstroke angle, along this x-axis. So for say 90-degree rotation of the cam during its outstroke, we can assume that every centimeter taken along this x-axis is equal to 15 degrees of cam rotation angle. So this 1, 2, 3, 4, 5 and 6 equal segments will ultimately be reflecting a total 90-degree rotation of the cam during its outstroke angle. So what we have done here is we have divided this total outstroke angle of the cam into equal number of even parts and named them as 0, 1, 2, 3, 4, 5 and 6. Now next what we are going to do here is we are going to draw the ordinates, that is the vertical lines from each of these points 0, 1, 2, 3, 4, 5 and 6, and length of this vertical line, that is height of this rectangle, is going to be equal to that is the total lift imparted to the follower or its stroke. So this is going to be the rise distance, which is equal to the stroke of the follower. So now the first point is, on the displacement diagram grid, draw a line from the beginning point of the rise or fall to the final point. So what we do here is we mark here at this that is the left bottom corner of this rectangle as point number A and the right top corner of this rectangle as point number C. So first we join the point number A with point number C. So here it is shown by means of this dotted line here. Now what we do next is we extend this line which is drawn here, that is the line AC, uh, and we draw a circle on this particular line having a radius r equal to s upon 2 pi, and this circle may be centered anywhere on that particular line. So second step is we have just extended this line AC below this rectangular box, so somewhat here, and we have considered here the center of the circle, and radius of this circle drawn here is going to be equal to s upon 2 pi, where s is nothing but the total lift imparted to the follower or the stroke of the follower divided by 2 pi. So what we do here is we first generate the line AC, that is the diagonal of this rectangular box, we extend it below, and then we generate a circle anywhere on this extended line. So it's not mandatory that we need to draw a circle right here or right here. Anywhere on this, depending upon that suitability of that particular sketch, we can draw the circle. So we have developed a circle here. Since we divided the abscissa, that is the outstroke rotation of the cam, in 6 number of equal parts, so we are also going to divide this the entire circumference of the circle into 6 number of equal parts. So that we have done here. This is 0 to 1 is the one part, second, third, fourth, fifth and sixth part, and we have numbered them accordingly: 0, 1, 2, 3, 4, 5 and 6. Then connect the circle divisions lines as shown in figure 1, 1 to 4 and 2 to 5. Now what we are going to do here is next that we will take the projection of all these points marked on the circumference of the circle, that is 0, the projection of this point on the vertical diameter of the circle. So basically it comes out at the center itself. Projection of the point number 1 taken on this vertical diameter, this is somewhat here. Projection of the point 2 taken on the diameter, it is overlapping with the projection of the point number 1. Then projection of the point number 3 on this vertical diameter, it is overlapping with the center of the circle, and same was the projection of the point number 0 and point number 6 also. Projection of the point number 4 taken on this vertical diameter is taken here, right here, and projection of the point number 5 taken on this vertical line is right here. So now next what we do is we that is developing the lines parallel to this one, parallel to the line or the diagonal line AC from these projected points. So projection of the point number 1 on this vertical diameter is at this location. We draw a line parallel to this particular line, the line AC, or extended up to the center of the circle. We draw this line and take its intercept at first ordinate. So this is going to be the first intercept. Then we move on to the second point. We take a projection of this. This basically gets overlapped with the projection of the point number 1. And again we draw one more line which is going to overlap this dotted line drawn earlier. But now we will extend this line up to the second ordinate. So the intercept obtained on the second ordinate is this much. Now we focus on the point number 3. We take its projection on this vertical diameter. It is at the center of the circle itself. We draw this line, we move along this line AC and take its intercept with the third ordinate. So this is going to be the intercepted value taken on the third ordinate. Now we focus on the point number 4. We take its projection on this vertical diameter. This is basically the point of projection, and then we start generating a line parallel to this particular line, and we will extend it up to the ordinate number 4. So this is going to be the intercept on the ordinate number 4. Then we take the projection of point number 5. We take its projection right here on this vertical diameter of the circle, and then we start developing or creating a line which is definitely going to overlap this one, but we will extend it beyond this fourth ordinate up to the fifth ordinate. So this is going to be the intercept which would be cut on the fifth ordinate by this projected line. And finally we look at the point number 6. The projection of the point number 6 on this vertical diameter is the center of the circle itself. Then we move along this path and we take it up to the sixth ordinate. So it basically meets this ordinate drawn from the point number 6 at point number C, and point number C is nothing but the total lifted position of the follower. So that is how. Now what we do next is we just draw a fine smooth curve passing through all these intercept values. So that is how we obtain this dark black curve. So this is nothing but that is a cycloidal curve. The follower moving in a cycloidal fashion will ultimately pass through all these locations at different cam rotation angles. So we have drawn this displacement diagram or the displacement curve for the follower during its outstroke angle only. For the return stroke, the similar type of the curve would be obtained, but it is going to be the mirror image of this particular displacement curve that we obtained for a follower during its outstroke.